Hi, everyone. Thank you so much for joining us today. This is our third webinar in our series, NOAA Fire Research from Conditions to Impacts, hosted by NOAA's Climate Program Office in partnership with the NOAA's Fire Observation Research and Services Team, or FOREST. Today we have some of our coordination team here on the call. We have Shiv Das, who's part of the Climate Program Office, and Anna Rita Mariotti, who's the Senior Advisor and Scientist here in the Climate Program Office. And I'd like to pass the microphone to her to open up our webinar today.
Well, welcome everyone. We are very excited to be hosting this webinar on this particular topic of climate and fire linkages. Just as a word of introduction, this webinar series has allowed us to sort of explore together the various things that NOAA is doing in terms of research to advance capabilities to understand conditions that lead to fire, understand how to forecast fires, as well as sort of understand the impacts that fire has. So we're very excited about this webinar series that involves speakers from our various labs under the OAR, Office of Oceanic and Atmospheric Research, as well as our various line offices and partners across the community that NOAA funds, including from our office. And so I'm very excited to kind of listen to what they have to say today, and also stay tuned for other webinars coming up. So back to you, Clara.
Great. Thank you so much for speaking on the goals of our series and the overarching series itself. So as Anna Rita says, this session will highlight research that is working toward investigating the links between fire and our climate and earth systems. So today we're going to hear from two scientists, Andy Hoyle from NOAA's Physical Sciences Laboratory and Rong Fu of UCLA. So during the webinar, at any point, please feel free to enter your questions with the question feature in GoToWebinar. And if you feel comfortable doing so, please indicate your name and your affiliation with your question so that I may let the speakers know who is asking each question. I'll facilitate a Q&A session after each presentation. So to start us off, I would like to introduce our first presenter, Andy Hoyle. Andy is a research meteorologist at NOAA's Physical Sciences Laboratory, and he leads the Monitoring, Predictability, Prediction, and Processes, or MP3 team in the Hydrology Applications Division. This presentation will focus on the relationships between El Nino Southern Oscillation and wildfires. So thank you so much for being here, Andy. We're excited to hear about this, and take it away.
Well, thank you very much, Claire, and thank you to the organizing team for inviting me. So I'm going to share my slides now, and I'll turn off my camera so you don't need to see me motion to an empty room here. So I assume you can see my screen here. And yeah, like Claire said, I'm presenting on the relationship between El Nino Southern Oscillation and wildfire area burn in U.S. Geographic Area Coordination Centers. And I'm presenting on behalf of a team composed of Physical Sciences Laboratory scientists and scientists from the Cooperative Institute for Research in Environmental Sciences at the University of Colorado Boulder, in addition to colleagues from San Diego State University. So where I'll begin right here is with the key points of our assessment of El Nino Southern Oscillation and wildfire area burned in contiguous United States Geographic Area Coordination Centers. They fall under three categories: our motivation, predictability, and physical mechanisms. So first, our motivation is that area burned varies greatly between time of year and geographic area coordination center. And this motivated us to identify aspects of the Earth system that are related to extensive area burn in advance. In terms of predictability, the two phases of ENSO, La Nina and El Nino, significantly alter the risk of extensive area burned in several contiguous United States Geographic Area Coordination Center regions, potentially rendering predictable future such occurrences. And then finally, with mechanisms, La Nina and El Nino are linked to hemispheric scale atmospheric circulation anomalies that influence regional precipitation and evaporative demand that are associated with extensive area burn. So the ability to accurately predict extensive area burned by wildfire well in advance would significantly assist in the strategic prepositioning of fire mitigation and suppression resources. This would help reduce the total area burned during several fire seasons, such as 2020, when fire consumed 10.1 million acres across the United States, resulting in economic damages exceeding $16 billion. 2020 was the third time that area burned exceeded 10 million acres since 1983, all of which happened in a 5-year span between 2015 and 2020. Noteworthy fire suppression efforts include those by the National Interagency Fire Center, a multi-agency collaboration hosted by the Bureau of Land Management, which separates the United States into several geographic area coordination centers, also known as GACs, 9 of which fall in the contiguous United States. And these GACs are shown here in the pastel polygons and include the Eastern, Southern, Northern Rockies, Rocky Mountains, Southwest, Great Basin, Northwest, Northern California, and Southern California regions. These GACs, they provide logistical and mobilization of resources throughout the geographic area and in coordination with other geographic areas where appropriate. Improved understanding of the causes of area burned in these GACs and whether those conditions could be anticipated many months in advance would inform these fire suppression efforts at the spatial scales at which the resources are organized. So on this and in many of the following slides, I'll briefly illustrate why wildfire area burn in GACs is so difficult to anticipate as motivation for our study. So here on the left and on this slide and others that follow, I've included a map of where the GACs are just for your reference. Also on this slide, you'll find area burned in 3-month overlapping periods on the horizontal axis here as a function of year on the vertical axis. This example here is for the Northern Rockies GAC. In 3-month overlapping periods, they include January, February to March, February, March, and April, and so on all the way to December, January, and February. And the years in our analysis include 1984 to 2022. And this is currently the last complete year of area burned from the Monitoring Trends in Burn Severity program, which is the data set that we're using here. So for the Northern Rockies GAC, as an example, wildfire area burn varies greatly between time of year and year. This is indicated by the magma shading on the plot. Note here that the shading begins at no area burn, which is indicated in gray. And the color bar here, it increases non-uniformly. And the reason for that is because wildfire area burn is pretty non-uniform between time of year, and GAC region. The Northern Rockies has a distinct fire season that spans the spring and the autumn, and wildfire area burn, it varies greatly between the time of the year and each of the 3 months periods within it. So now I'm going to bring in wildfire area burn during 1984 to 2022 as a function of 3-month periods in the 8 other GAC regions in the contiguous US. I think this perspective really allows us to fully appreciate how complicated wildfire area burned is, as it varies greatly between time of year, and GAC region. I'm not going to dwell on the picture because we could spend a few days discussing all of the interesting features. I will, however, use it to motivate our study and to pose the central question here. Can we identify some aspect of the Earth system that is related to extensive area burned many months in advance that could offer potential predictability of wildfire resource management? So here we look toward the El Niño Southern Oscillation as an aspect of the Earth system that may offer that potential predictability of extensive area burned by wildfire. So we're going to diagnose relationship between ENSO and extensive area burned in these contiguous United States GAC regions. We do so by relating ongoing La Nina and El Nino occurrences during 3-month periods to area burned by wildfire during following 3-month periods in each of the 9 contiguous United States GAC regions during 1984 to 2022. So visual representation of La Nina and El Nino events are shown in this image on this slide, based on the catalog created and maintained by colleagues at the NOAA Climate Prediction Center in their operational definition of the El Niño Southern Oscillation. This perspective shown in this image shows on the horizontal axis the 3-month season of interest, so January, February, March, and April, and so on all the way to December, January, February. And on the vertical axis, each year, 1984 to 2022. A blue polygon means that a La Nina event was ongoing, a red polygon, an El Nino event was ongoing, and gray, meaning that there was neither an El Nino nor a La Nina. So let me provide 2 examples real quickly, one for a La Nina and one for an El Nino. So in 1984, La Nina event began in September to November and extended into 1985, ending in July, August, and September. And then in 1986, an El Nino began in August, September, and October and extended all the way into 1988, ending in January to March of that year. So our main metric here is the relative risk ratio, and we're going to use that to assess links between La Nina and El Nino and conditions in each of the geographic area coordination centers that we have, which includes extensive area burned, high evaporative demand, and low precipitation. Area burned is our target, and it's obvious why we examine it. We also examine evaporative demand and precipitation to quantify the demand and supply of moisture to vegetation by the atmosphere, respectively, thus making vegetation more or less likely to burn. Evaporative demand is the demand side, also known as the thirst of the atmosphere, and it quantifies how much water the atmosphere is demanding from the land surface and vegetation. It's used widely in the wildfire community and includes contributions from temperature, vapor pressure deficit, wind speed, and downwave shortwave radiation. We derive evaporative demand from the North American Land Data Assimilation System version 2, and precipitation from NOAA and CEI's NCLIME grid. So the relative risk ratio, it compares the frequency of an event related to two different conditions, which allows us to determine if an event is more or less likely to occur related to one condition than another. If a relative risk ratio is different from one, then it means that event is more likely to occur under one condition than another. So the relative risk ratio is computed as follows. First, we identify our events, which in each geographic area coordination center is extensive area burned, high evaporative demand, and low precipitation. Extensive area burned is defined here as area burned exceeding the 66th percentile. High evaporative demand is defined here as precipitation exceeding the 66th percentile, and low precipitation is defined as precipitation falling below the 33rd percentile. We've chosen these thresholds here to align with how seasonal forecasts are typically expressed, that is, using terciles. Next, we group our events based on conditions. That is, we group our events based on whether a La Nina was occurring or not, and whether an El Nino event was occurring or not. Then we compare the two groups to compare the relative risk ratio. So I'm going to take you through a couple slides where I'm going to provide an example here. So I'm going to illustrate the relative risk of extensive area burned related to January to March La Nina based on the example from the Southern Geographic Area Coordination Center. So the illustration here, it follows three steps. The first thing we do is we identify La Nina in January to March. We identify extensive area burned from that set of La Nina events, and then we compute the relative risk ratio. So first, in January and March, there were 14 La Nina events in the history that we're using from the Climate Prediction Center. They're listed here on the slide. The remaining January to March seasons, 25 of them were not La Nina events. Next, from those La Nina events and non-La Nina events, we identify whether there was or was not extensive area burned. So examples without extensive area burned have a line or I've struck them through just to illustrate how many seasons there were in there. So the 14 La Nina events, 7 were found to be related to extensive area burned. Of the 25 non-La Nina events, 5 were found to be related to extensive area burned. So 7 out of 14 and 5 out of 25 are our two sets. So now let's compute the relative risk ratio. So the relative risk ratio is the ratio of the frequency of extensive area burned during La Nina events compared to non-La Nina events. So the frequency of extensive area burned during La Nina events is 7 divided by 14, or 0.5. And the frequency of extensive area burned during non-La Nina events is 5 divided by 25, or 0.2. So the relative risk ratio is 0.5 divided by 0.2, or 2.5. This indicates that January to March La Nina is related to a 2.5-fold increase in extensive area burned compared to non-La Nina. So a reasonable question that someone could ask is whether these relative risk ratios are meaningful in any way. That is, could these results have been obtained by random chance, given sampling and so on and so forth? We tested that and computed the probability that our results could have been obtained randomly based on bootstrapping. So bootstrapping is a common technique, and it involves randomizing data with replacement, performing a given calculation, and repeating it 10,000 times, then computing the likelihood that a random result was obtained in the 10,000 iterations. So for us, conditions with a less than 5% chance of occurring randomly are considered meaningful and are noted in the results that I'll present in the following. So we examine ENSO-related conditions across 11 3-month periods following La Nina and El Nino events in a given 3-month period. And the image on this slide is a visual representation of that, which indicates the 11 3-month periods on the vertical axis, which succeed a 3-month period during which La Nina or El Nino events are ongoing in the horizontal axis. So let me use January to March once again, the left column of the image as an example. So what we do is we assess conditions in the concurrent January to March, indicated as a 0 here in the first row of the image. We then assess conditions in the following 3-month periods, moving upward in this image here, with 1 indicating the following February to April, 2 indicating the following March to May, and so on, all the way to 11 3-month periods succeeding that January to March El Nino or La Nina, which happens to occur with the following December to February. So let me go through another example again. Let's use February to April as another example. So we assess conditions in the concurrent February to April, indicated as 0 in the first row of the image. The second row of the image is 1 subsequent season, so that's the following March to May. 2 indicating the following April through June, all the way to 11 indicating the following January to March. So we repeat this for all the remaining 3-month periods within El Nino or La Nina that you can see here in the horizontal axis as a function of all these subsequent 3-month periods. The colors are shown in this image as a visual aid to show how the 3-month periods are organized. So you can see here that they form these diagonal striations in the image here. All right, let's get into some results now. So again, I'm going to do a little bit of illustrative tasks here before really getting into the results. So the perspective is shown here in practice for the relative risk ratio of extensive area burned. So this is for 3-month periods that follow La Nina event on the vertical axis as a function of those 3-month periods on the horizontal axis here. The deeper the reds indicate a higher relative risk of extensive area burned. The deeper the blues mean the opposite, indicate a lower relative risk of extensive area burned. Or once again, extensive area burned means we're just exceeding the 66th percentile in the historical record. You might note a white dot here. The white dot indicates that the relative risk is unlikely due to random chance. That is a chance that the result that we obtained here occurred randomly in less than 5% of those bootstrapped examples. So let's use January to March, La Nina, in the left column of the image as an example, just like the prior slide. So for the concurrent January to March, indicated by 0 in the first row of the image, there's a greater than 2.5-fold increase in the risk of extensive area burned, which is unlikely due to random chance, indicated by that dot right there. The large increases in the risk of extensive area burned are found to occur up to 6 3-month periods following a January to March La Nina. So what this means here is that La Nina in January to March increases the risk of extensive area burned from winter through the following early spring. So a common feature among these results that I'll show are these diagonal striations in the results that you'll see here. This indicates an increase in the risk of a given condition, in this case area burned, in a given 3-month period related to a persistent La Nina event. So these are common features that you'll happen to see. All right, let's look at some results here, and we'll look at it for one region. This is the southern region. So what we're doing here is we're looking here at the risk of extensive area burned in the top row, high evaporative demand in the middle row, and in the bottom row, the risk of low precipitation. And we do this simultaneously for each region to give an idea of how this extensive area burned is related to given physical mechanisms. So on the right here, you'll find these color bars. These are the color bars that correspond to each of the given relative risks of area burned, evaporative demand, and precipitation here. So if you want to look and see what that value is, you just look over there to the right. So the main takeaway here is that La Nina is related to an increased risk of extensive area burned across several subsequent 3-month periods in the southern GAC region. This is indicated by relative risk ratios that are greater than 1 and are unlikely due to random chance during 3-month periods that follow a summer, autumn, and winter La Nina. The increased risk of extensive area burned after a La Nina in this GAC region is linked to a heightened risk of both high evaporative demand and low precipitation during the intervening 3-month periods, which contribute to the desiccation of vegetation, making it more prone to burning. So specifically, summer, autumn, and winter La Nina significantly increase the risk of extensive area burned. The elevated risk can last for up to 10 3-month periods, extending past following a spring La Nina event. So there's a greater than 3-fold risk of this extensive area burned in the 3-month periods following this La Nina. And this heightened relative risk in the southern region is linked to both this high evaporative demand and low precipitation. The implication here is that La Nina can be used as a predictor of extensive area burned in this Southern Geographic Area Coordination Center region. And this provides forewarning of extensive area burned following an autumn, winter, and spring La Nina event, and that the local physical mechanisms here happen to be related to evaporative demand and precipitation. So let's move on here to another GAC region here. Let's move on to the southwestern region. And the southwestern region really, it shares a lot in common with the southern region, at least in terms of how this relationship plays out with La Nina. So what we're seeing here is a risk of La Nina persisting from summer through early spring, and that persistence there is related to an increased risk of area burned. So in the Southwest GAC, this increased risk is related to both high evaporative demand and low precipitation during following 3-month periods. The main takeaway here, once again, is that autumn through early spring La Nina provides similar predictive power of extensive area burn in the southwestern geographic region as it did for the southern region. There is, however, one noticeable difference here between the two regions, and I'm outlining this right here with my cursor. This notable difference is that in the southwestern GAC, autumn, winter, and early spring La Nina is associated with a decreased risk of extensive area burned in the following late spring and early summer. That's noted here by the decreased risk, the blue shading once again. The reduced risk is associated with decreases in the relative risk of both high evaporative demand and low precipitation during intervening 3-month periods. That is, La Nina is related to above average precipitation and below average evaporative demand, reducing the risk and really preventing vegetation from drying out. Now let's work in the Rocky Mountain, which again shares a lot in common with these other two regions that are shown here, that being the southern and southwest. So the Rocky Mountain region, this is here on the right-hand column. These similarities can be found in terms of the sustained elevated risk of extensive area burn following summer, autumn, and winter La Nina. The increased risk of extensive area burn is related to increases in the risk of high evaporative demand and low precipitation in the intervening 3-month periods between the La Nina and following into the early spring. It's important to note that the Rocky Mountain region experiences a dry season. That is one in which little precipitation is observed in late fall and winter. And you can note that here in the bottom right-hand panel, where we have this gray shading. So that gray shading just indicates that that 3-month period contributes less than 5% of the annual total of precipitation. One notable difference between the Rocky Mountain region and the Southern and Southwestern Geographic Area Coordination Centers is that La Nina in late winter and early spring is related to a decrease in the risk of area burned between 9 and 11 3-month periods in the future, which is related to a decreased risk of low precipitation during that time. Well, I'm running a little bit low on time, so I won't be able to describe all the relationships with La Nina in each of the Geographic Area Coordination Center regions, nor will I really be able to get into El Nino, but I'm happy to share all those results, so please reach out if you're interested. Happy to share these slides, this presentation, and also the journal article that we will shortly submit. So one set of GAC regions that I'd like to touch on related to La Nina is the northern tier GAC regions in the Northwest, Northern California, and Great Basin. Really touching on this here, summer through winter La Nina is associated with an increased risk of extensive area burned in all 3 of these GAC regions during the following spring and summer. And this increased risk is indicated by relative risk ratios exceeding 1, and those again are unlikely due to random chance. So the increases in the relative risk that form these diagonal patterns many 3-month periods after a La Nina event. And one thing to note here is the distinct fire season within these GAC regions, as you can see here, there's a time of year in which they don't really see that much in the way of area burned, which is indicated here by the gray shading. The regional mechanisms in terms of the risk of high evaporative demand and low precipitation appear to differ a little bit between these geographic area coordination centers, despite similar elevated risks of extensive area burned. Though the seasonality differ, the mechanisms appear to involve a decreased risk of high evaporative demand and low precipitation in the autumn and winter, which could enhance vegetation growth that's more prone to burn during the following spring and summer. So a common theme from the regional perspective that I presented is that late calendar year La Nina is related to an increased risk of extensive area burn in following 3-month periods. So what I'll show here is hemispheric conditions that link La Nina late in a calendar year to changes in the relative risk of extensive area burned, high evaporative demand, and low precipitation in these contiguous United States geographic area coordination centers during the following 3-month periods. So these remote physical drivers, they include sea surface temperatures in the top row of this plot, tropical precipitation in the middle row, and in the bottom row, 250 hectopascal geopotential height, based on average anomalies during that 3-month period, where an anomaly is just a departure from the average. So what we're doing here is we're showing these conditions following October to December La Nina events. So for example, conditions in October to December in this left column are averages of anomalous sea surface temperatures, precipitation, and geopotential height during La Nina events in that 3-month period. In conditions in the following January to March, this is the second column here from the left, there are conditions during January to March when we have a La Nina event during October to December. So let's bring in the other 3-month periods here that are relevant to this analysis. So La Nina events late in a calendar year, they're linked to persistent hemispheric anomalies that are associated with these significant changes and related to the elevated relative risk of extensive area burned in many of these geographic area coordination center regions. La Nina events are indicated by sea surface temperature anomalies in the tropical central and eastern Pacific Ocean. You can see that here by the contrasting below average sea surface temperatures in the central Pacific and the above average sea surface temperatures in the western Pacific. La Nina events are also associated with precipitation anomalies, and that's in the middle row here in each of these plots. And this is really indicative of the tropical atmospheric forcing that is imposed by a La Nina event. And this is indicated by these contrasting precipitation anomalies between the central and the western Pacific Ocean. It's these tropical precipitation anomalies, the atmospheric forcing, that then drives atmospheric waves, indicated by 250 hectopascal geopotential height anomalies. And these persist through the following spring. And you can see here that over the Pacific North American region, in the concurrent October to December, proceeding all the way into early to middle of the following year, you can see these high pressure areas that set up over the western and southern United States. That right there is related, and closely related, I would say, to the risk of extensive area burned over the geographic area coordination centers that I had highlighted previously. So sensing that my time has ended, I will linger here on the main takeaways and thank the organizers for giving me the opportunity to speak and for all of you for listening. Thank you.
Thank you very much, Andy. That was great. We have a couple of questions coming in already. I invite folks to please enter in more questions as they come to you, and we'll have a couple minutes of Q&A here. So our first question comes from Taylor West, a NOAA fellow attending the University of Maryland, Baltimore County, and pursuing a PhD in public policy. So this question is a bit more geared toward mitigation and predictions that can lend themselves to mitigation. So this question says, according to the 2025 State of the Air Report, pollution is moving back east. Since the factors affecting pollution from these fires differ based on location, will there be different mitigation tactics to inform people? Andy mentioned knowing months ahead that there could be these fire events. Is this consistent for the East Coast? And if so, how are we currently using this information for mitigation?
Well, that's a bit outside of my wheelhouse. In terms of, I'm not an air quality expert. I rely on probably the same experts as you do for for that information. So I'll politely defer to those experts because I don't think anybody needs to hear from me on that topic.
Okay, thanks, Andy. Good question. We'll keep investigating it elsewhere. We have another question from John Lanzanti from GFDL. Have you looked at climate models to see if they reproduce patterns of precipitation and evaporative demand?
Totally. Yes, we have. We've used your SPEAR model. We've used several other ones as well to confirm these results right here. So they're very consistent across models and observations.
Great. Another question. This suggests that the predictability of evaporative demand may be key to uncovering additional skill in S2S forecasting area burned.
Yeah. Evaporative demand is an understudied quantity, I would say, and its predictability follows that. There have been some really nice studies that have come out that have indicated the predictability of evaporative demand, and it's sort of contributing variables like temperature and vapor pressure deficit, which all sort of feed into this study right here and indicate that predictability is pretty high. And a lot of those studies do indicate the predictability of evaporative demand actually is quite a bit higher than that of precipitation. So I think in the prediction community, we need to rely on that quantity a little bit more, not only in terms of fire, but also in terms of drought.
Okay, great. One other question. Beyond the established correlation, how well can we currently forecast the timing and location of peak fire activity within a specific GAC, like the Southwest or the Southern area, based on an ENSO forecast made 3 to 6 months in advance?
I would say you're probably not going to be able to pinpoint the location of your fires. Those locations of fires, both in terms of where they are spatially, but also temporally, they're pretty tough because they depend upon a lot of quantities that we aren't able to forecast at those lead times. The ENSO relationship is a pretty suitable one here because I think that there's a real convergence of the regional scale drivers that relate ENSO to the United States and these contiguous United States geographic area coordination centers. So this forewarning is really appropriate for this scale, but I don't think ENSO will really gain you much in terms of being able to say, well, the last week of August, you're going to be able to see an increased fire risk at this location because of ENSO.
Okay, thank you so much. We are running low. The final question I'll share is how can we keep in contact with Andy or his work? And with Andy's permission, I can put his email in the chat box if that works.
That works. You could also probably type in my name into your favorite search engine and find out that way. It works pretty well.
Okay, great. All right, thank you so much. If you have more questions for Andy, please put them in the question box and I will relay them to Andy afterwards. Totally. So thank you again so much, and we'll move on to our next presenter. So Rong, you are now the presenter and you can go ahead and share your screen. So our next presenter will be Rong Fu, a climate researcher and professor in the Department of Atmospheric and Oceanic Sciences at UCLA. In 2020, Rong was awarded a grant from our Modeling, Analysis, Predictions, and Projections, or MAP program, to pursue research on the interaction of large-scale atmosphere, land surface, and fire. So the presentation today will be on how drought and hot weather influences wildfires in the Western US. And we're very excited to hear about this work. Go ahead, take it away.
Okay. Can you hear me?
Yes, we can hear you.
Great. First of all, I really like to thank Climate Office and also this fire webinar to give me this opportunity. And as Clara mentioned, this work was largely supported by the Climate Program Office. And I want to say that the Climate Office awarded my first grant when I started as assistant professor was from Climate Office. And I think that really set my career. I think it's really enabled my career to take off. And over the last 30 years, the support from Climate Office has been crucial for my career. And I hope the early career scientists, middle career scientists, will continue enjoying the support by Climate Program Office as I did, as I enjoyed throughout my career. And I want to acknowledge my co-author, Dr. Yizhou Zhuang. He was supported by the Nobel Grant when he was a postdoc. And the result I showed are produced by him. He's now a professor at Hong Kong Baptist University. And living in the West, Southern California, and the fire impact is really up close. As you all know, that this January Los Angeles fire has been probably the most costly natural fire in the U.S. There's 30 casualties, and the cost is estimated around 250 to 275 billions with B. I still remember when I walked at night, a third of the sky was red. It's very much like the scene we see in Gone with Wind, Atlanta fire. And the fire the fire impact is not limited to the economic impact, to things we can put value on. It also threatens things that's invaluable to us and to our soul. For example, this photo shows the General Sherman, the world's largest trees in Sequoia National Park was threatened by fire. For those who were fortunate enough to standing in front of this tree, and we cannot help to feel so humbled by this wonder created by our planet Earth. So this is just real quick that the fire over Western U.S. Has increased dramatically in the last 20 years. And in fact, the most of the increase is in the warm season from May to September. And the impact, so the burned area is more than doubled. And the impact of Western US fire is not limited to the Western US, as you can see from the satellite image. The smoke generated by California fire and can pollute air across the country all the way to the northeast part of the US and even Canada. It's not just the large fire that threaten us, and the fire has been constant threat. For example, this morning I look at the fire information. As we speaking now, there are 49 large fires burned across the U.S., and there are more than 15,000 firefighters and support personnel are working on suppress these fires. And this year, up to now, more than 3.7 million acres has been burned, and this is larger than the size of the Connecticut. And Andy gave a great explanation how VPD, vapor pressure deficit, affect the fire. So for fire, we depend on two things, on the fuel load and the flammability, as well as the right weather condition. And the fuel load is largely depend on the vegetation conditions, and that include the forest management on the fuel load, as well as the long-term vegetation dynamics. The flammability, however, is mainly dependent on the climate and the weather, and also the actual occurrence of the fire is very much affected by the weather condition, and basically higher temperature, low humidity, and the wind. Most of fire are ignited by human. Actually, the lightning strike the fire are not as much as human-induced fire over the Western U.S. Again, Andy gave us such good explanation how the vapor pressure deficit affect the fire, and I will just go through here to reinforce what he said. And this is the data. There's overwhelming evidence show that the vapor pressure deficit is the leading environmental condition for burned area over many parts of the world, include the Western U.S. So here is a study by William et al. Shows that. And again, Andy mentioned the VPD is more predictable, and in part because the VPD is not just depend on moisture, it's depend on temperature. Over Western US, I hope through this presentation to show is actually more influenced by temperature, which is good news in terms of potential for prediction, because we can predict the temperature much better than predicting rainfall. So basically, when you increase the vapor pressure deficit, and the plants lose more moisture as they open the stomato, inhale the CO2, because within the stomato, the vapor, the water vapor is close to the saturation vapor pressure, which is determined by temperature. This is ES. But when they open it, the amount of the moisture plants lost from stomato is depend on the difference, the gradient between what's inside of stomato and what is in the air next to it, ambient air. So the larger VPD is, the more moisture plants lose, and that's why they become water stressed and reduce the plant moisture under high VPD. And of course, wildfire is not new. It's part of the Western landscape over Western US. Historically, they are a great example how actually climate change, in this case, it's a natural climate change, affect the fire. For example, the historical record found over my favorite place, Tarpat in Los Angeles, show that the large scale fire happened at the end of last glacial maximum and has contributed to the extinction of many giant beasts such as saber-toothed cats, giant sloths, American camels. And that's because when climate is become warming and drier, as it come out of the last glacial maximum towards the interglacial maximum, and the human start to set fire, and these fire become uncontrollable and forever changing the landscape of Western US from woodland ecosystem to more of a chaperone. So that really raises question, what caused rapid intensify of fire weather and drought over Western US in recent decades? Are they part of the natural cycle, natural climate variability, or there's something else? So the main message of this presentation is to show that really the increase of atmospheric vapor demand, which is vapor pressure deficit, VPD, that Andy talked about, is mainly due to warmer surface temperature. Actually, it's a 2/3 to 3/4 attributable to warming of temperature in the since the turn of the 21st century. So how do we determine this? And there are many studies use climate model to show this already. But since I'm an observational researcher, I would like to complement those modeling-based attribution with observational-based attribution. So here is what we do using the example, for example, the August complex fire, which is the largest fire over California in the recent history. And so that fire is associated with unprecedented higher VPD. And you see 100 percentile, that means it's never happened before. And the question is, so for this VPD, we can ask a question, to what extent the weather pattern we can explain, to what extent we can explain this unprecedented VPD by the weather pattern happen at the same time. And so now we can see this is the 500 hectopascal joule potential height happened on the day when August complex fire start. And we do see this really strong high pressure system. And in fact, at the center, it reaches 3 sigma, meaning this is more than 99 percentile. The question is, for this very strong higher pressure system, how much we can explain what we experience on the ground based on this weather system. So what we did is we go back to historical record and find a weather pattern very similar to what we're seeing on the day August complex fire happened. Of course, we cannot find exactly same weather pattern, but we can find a set of very similar pattern. And then we can use those pattern and associated VPD to reconstruct this circulation pattern and associated VPD using machine learning approach. And this is what we got. Basically, yes, we would see very strong VPD 95 percentile, but we wouldn't see as strong as we actually observed on that day. So now the cause of a wildfire, increase of fire weather, and this is the top is a vapor pressure deficit, which is the black dotted line, and the histogram pink one shows the burned area. The main message here is both burned area go with increase of VPD. They're quite well correlated, just as Andy showed in his presentation. And here is a spatial pattern. You can see most of the increase were stronger over the southern part of the western US. And the middle panel shows the increase of VPD due to increase of temperature, which is saturation vapor pressure. So that increased steadily. And the atmospheric moisture, which is the actual vapor pressure decreased, but it's insignificant. The decrease is insignificant. And they're mainly limited over Southwest US. So if we look at to what extent the atmospheric circulation change can explain the increase of VPD, and we can look at this map. So here is a ratio of VPD increase that can be that's linked to change of atmospheric circulation versus the observed VPD. So over most of Western state, and you see 25% to 46%. On average, about 30% of increasing VPD during the warm season, which is May to September, can be explained by the weather pattern changing, atmospheric circulation change. The rest of them are really due to warmer climate, especially the warmer temperature. So now the increase of a fire also need a fuel. And I want to mention that the drought persistent through Western US has contributed to this. And we know that drought happened in the history of Western US. We had a mega drought, decadal mega drought. But a recent study by Park Williams shows that in terms of soil moisture, we are in the mega drought that is comparable, if not worse, than the worst mega drought in the last millennium, based on the compared to paleoclimate. Each drought kills millions of or hundreds of millions of trees. For example, 10 to 16 drought and more than 100 million trees killed in California alone. And in the 2022 drought, more than 36 million trees killed in California. And these dead trees create a massive fuel load for the fire. And now, what caused this drought? We know drought can be caused by decreased precipitation and or increase of evapotranspiration. If we look at the Western drought, the drought intensity, which is represented by the combined precipitation deficit and the increase of potential evapotranspiration, and basically increase of atmospheric vapor demand. And the drought intensity as measured by this matrix has increased 35% over the US since 2000, and the drought area increased 17% over US. More importantly, if we look at this graph, where the black line is total drought intensity, blue line is the drought intensity due to reduced precipitation, and the red line is drought intensity due to increase of evapotranspiration. And prior to 2000, the black blue line are pretty much on top of each other, which says the drought is mainly due to precipitation deficit. The red line has much smaller magnitude, ranging from 20 to 30% of the total drought intensity. But as we enter 21st century, the red line start to catching up, and to the point in the last decades, the red line is about the same magnitude as blue line, and when they add together, the drought intensity almost double. And similarly, in terms of a drought area, you can see that in the last 20 centuries, and the blue line, red line follow each other closely, meaning the drought area are mainly due to precipitation deficit. The red area, meaning the drought area caused by increase of evapotranspiration, potential evapotranspiration, are much lower than the precipitation that caused by precipitation deficit. But this has changed in the 21st century, where the red line is catching up with the blue line. In fact, now the increase of potential evapotranspiration contribute 57% to the total drought severity and 66% of the area. So here is one example how the changing of the temperature and precipitation affect the last drought, 2021 to 2022 Western drought. So this is observed combined precipitation and the potential evapotranspiration. And we can see that large area of Western US was classified as a D3 and D4 drought. However, if we're only looking at the drought severity due to the atmospheric circulation change or natural climate variability, and the drought is much less severe. It's less severe, and drought area is similar, and observed drought covers 92% of Western US in our analysis, and almost 60% area experience equivalent to D4 using our basically 2 percentile using our matrix. But if we only consider atmospheric circulation caused drought, most of the area still will experience drought, 71% of the Western US in this domain. But most of the drought would be from moderate to anomalous dry, much less than what we observed. So to conclude, the increase of atmospheric evaporative demand, or VPD, mostly due to warmer climate, has contributed about 2/3 to 3/4 to the observed intensification of fire weather and the drought that include both severity and area. And for specific large events, for example, the largest fire in California in the August, the August fire, August complex fire, and a third to a half of the extreme fire weather is due to warming of the climate, warmer temperature, and to the exceptional drought over western U.S. occurred during 2020 to 2022. The warmer temperature and warmer climate also contribute about this much. And with that, thank you very much, and I'm open for questions.
Thank you so much, Rong, for that great presentation. I'll encourage the audience to please submit your questions. And again, if you feel comfortable, please share your name and your affiliation with your question, if I can share it with the speaker. There's one question, more general methods question to start us off. You did mention that machine learning can be part of the methodology to separate the influence of natural variation from that of climate change. Can you comment a bit more on how machine learning tools help with this research and its limitations?
Yes, thank you. The way we use machine tool is we use the machine learning to recognize the similar pattern. For example, when we show that when we show the example in the fire, so it's let me see, it's the August complex fire. We want to find a similar circulation pattern. What we did is we use machine learning to go back to the weather data, 500 hectopascal geopotential high, the record, and to find a pattern that's very similar to this. And then, so this is done just by machine learning, which is really good at recognize pattern. And then we can construct circulation that is very similar to what we observed on that day. And so limitation here is we're limited by what we can find in the historical record. And so I know we're in a climate that changes rapidly. Our record is not long enough to capture all the extremes. This method in part overcome that limitation by we're trying to construct the circulation that is as close as what we observed. However, our construction method is often limited in terms of capturing this really strong, non-linear response of surface condition to the extreme weather pattern. So as such, we probably underestimated the influence of a weather pattern in this case.
Okay, great, thank you. Another question, what do you consider the most critical next step in the research? Better observations, improved modeling, or integration across scales, or do you have other ideas?
I think a very important step, given the profound impact of fire, what Andy presented is important. We need to be able to predict and help society to prepare for the coming fire season. And I really think, as Andy said, the impact of the VPD, I would say particularly temperature, has been underappreciated. We're trying to focus on predictability of precipitation, which is really hard on seasonal longer time scale. But for fire weather, perhaps we don't have to, that's important in terms of growing, for example, leaves. But in terms of fire weather, I feel we should further understand, explore to what extent we can extract predictability from temperature prediction. In terms of observation, I really think the maintain the quality of our observation are extremely important. And also, I would say that when you talk to fire manager, one thing we hear quite a bit. Andy probably know this more than I do. Is the spatial coverage and lack of observation, because fire is very local, and especially in the mountain area, the observation in the valley is very different from mountain slope. And I think it's really crucial to strategically add observation in the area where it really represents the fire, the weather condition that's crucial for fire.
Great. Thank you so much. I think we are out of time for today, but I want to thank both of our speakers again for sharing their presentations today. The recording of this presentation will be up on the Climate Program Office website at the link that I shared in the chat. And if you have any questions about the series or for the presenters, feel free to reach out to me. And that will conclude our webinar today. We hope to see you at a future webinar. Our next is scheduled for Wednesday, September 3rd, 2 weeks from today, from 2 to 3 p.m. Eastern. And we'll be hearing from two speakers who will talk about the impacts of wildfires on air quality, from information from the FireX joint NASA NOAA field campaign. So again, thank you so much for joining us, and we hope to see you next time.
Thank you.